So this video is going to discuss a few additional theorems about chords of circles, and that will include Theorem 10.4, 10.5, and Theorem 10.6 in the geometry textbook. Theorem 10.4 states that in the same circle or in congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. So in other words, if we take a look at this diagram here, the minor arc AB is congruent to minor arc BC, this is AB, and this is BC. They are congruent only if line segment AB is congruent to line segment BC. Now if and only if goes both ways. So what we can do is we can first assume that AB arc is congruent to arc BC, and then try to prove that line segment AB is congruent to line segment BC, and then we would go the other way. We would assume that line segment AB was congruent to line segment BC, and then try to prove that the measure of arc AB was equal to the measure of arc BC. So let's go from left to right first. Let's assume that the measure of arc AB is equal to the measure of arc BC. That's the same thing as saying that arc AB is congruent to arc BC. Well, for their measures to be the same, that would have to mean that their central angle, or the central angle that intersects the arc, would have to be equal. So we would have to have this central angle, whoops, let's try to get back to the center here again, that we'd have to have this central angle equal to this central angle. Those two angles would have to be equal if the arcs were equal. Now we also know that if we call the center of the circle, let's say O, let's say we call the center of the circle O, that the line segment AO is a radius, so it would be equal to, in length to the line segment OB, which is also a radius, which in turn would be equal to the line segment OC. So we have all these three sides of these triangles being equal. Now if we take a look and see what we have now, is we have two congruent triangles. We have triangle AOB and triangle BOC, which we can now prove are congruent. We can prove that they are congruent actually because we have side, angle, side. So we have side AO is congruent to side OC. We have side OB of triangle AOB is the same or congruent to side OB of triangle COB. So we have two sides. These two sides are congruent to these two sides. And since the measure of the arc was equal, these central angles are equal as well. So we have side, angle, side, or we have side, angle, side. We have two congruent triangles, and because we have two congruent triangles, we can then conclude that side AB of triangle AOB is congruent to side BC of triangle OBC. So we now have AB is congruent to BC, which was proving from left to right. Now, to prove from right to left, we have to now make the assumption that line segment AB is congruent to line segment BC, and then prove that the measure of arc AB is the same as the measure of arc BC. So in this case, we actually have the diagram correctly annotated. We're assuming AB is congruent to BC, so we have equal marks on both of these, and we now have to prove that the arc AB is congruent to arc BC. So we make some of the same observations that we made before. If the center of the circle is an O, then we have a line segment AO, because it's a radius, is congruent to line segment OC, which is congruent to line segment OB. These are all congruent. Having made all of these congruent, and also noting that AB is congruent to BC, we see that by the side triangle postulate, we now have the triangle AOB is congruent to triangle BOC. Because these two triangles are congruent by side, we also know that their angle AOB, the corresponding angle AOB in the other triangle, is BOC. These two angles are congruent. We can draw congruence of those two angles. And angle AOB is the central angle that intersects arc AB. Angle BOC is the central angle that intersects arc BC. So because these central angles are congruent, we can then prove that arc AB is congruent to arc BC. And that is how we complete the proof of Theorem 10.4. The next theorem to prove is now Theorem 10.5. This theorem states that if a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord in its arc. So we know in this theorem that we are given a diameter, and we are given that the diameter is perpendicular to a chord, and then we must prove that if that is all true, then line segment DE is congruent to line segment DF, and also that arc DG is congruent to arc GF. So let's see how we can prove that. We know that this is a diameter. We know we'll call the center of the circle again. Let's call it O. So we have O as the center. At this point, we can draw radii if we wish. A radius from O to D, and we can also draw a radius from O to F, like such. So we've just drawn two radii from the center of the circle, and we know that all radii are equal. So we can say that this radius equals this radius. Oops, we seem to have lost the other radius, so why don't I redraw that one here. Okay, that radius equals this radius in length. So now we have OD is equal to OF in length. So we have that congruence because it's a circle. We also have that these are right angles, that the diameter intersects DF at a right angle. So we have two right triangles here, one of them being on the left and one of them being on the right. We already know their hypotenuses are equal because OD and OF are the hypotenuses of these triangles. And we can also see that the shared common side is congruent to itself because of reflexive property. So because of hypotenuse leg, and again we seem to have lost the triangle, let's move it right back here. Again, due to hypotenuse leg, we have congruence of the hypotenuse. We have this leg that is shared in common. Now we have proven that we have two congruent right triangles. Since the right triangles are congruent, we know that the central angles up here, angle DEG, which would be this angle here, is congruent to angle, actually DOG is congruent to angle GOF, which we could have over here. A little bit hard to see at this point. We've got a lot of lines cluttering. But basically, this central angle is equal to this central angle, which means that the arcs DG and GF are congruent. Well, that was one of the things we needed to prove. We also needed to prove that DE is equal to EF. And since we have the fact that these are two congruent triangles, we therefore know that the corresponding sides are congruent. So DE is congruent to EF. So once again, I just want to recap the proof without all the clutter. Basically, once we draw the radii from the center, like such, and again like such, we end up having two congruent right triangles. The congruence of their central angles leads to the conclusion that the arcs DG and GF are congruent, and the congruence of the corresponding sides, which would be DE and DF, proves that DE is congruent to EF. So that leaves us with just Theorem 10.6 to prove. And Theorem 10.6 states that if one chord is a perpendicular bisector of another chord, then the first chord is a diameter. Rather than clutter up this drawing, I'm going to give you a rational explanation for why this is the case. The way to prove this theorem is to assume that the first chord is not a diameter, in which case you then would find the diameter that goes through this point, the point of the intersection of the two chords. You would have to find the point that goes through the intersection of those two points and also goes through the diameter. Well, we know that if we take the point from the center of the circle that is perpendicular to this chord ML, that we will bisect ML because of Theorem 10.5 that we just proved. That would imply that if JK was not a diameter, that then we would have two lines through this intersection point, both of which were perpendicular to chord ML. But we know from a theorem, or actually a postulate, which is called the perpendicular postulate, that given any point not on a line and any line, there is only one point that is perpendicular to the given line through that point not on the line. So therefore, that point not on the line must be the diameter. And that is sort of the thinking behind how we prove Theorem 10.6.